Look, I've got a piece of advice for you. Maybe the most important advice I'll ever give you. Imagine you're walking down the street, say somewhere in Midtown New York or right here in Pasadena, and suddenly you see a guy walking toward you. And this guy looks exactly like you. He's got the same raincoat, the same haircut, the same surprised look on his face. Maybe he's even good looking, just like you. You get closer, and he extends his right hand to say hello. But here's the weird thing. He extends his left hand, like in a mirror. So, here's my advice. Do not shake his hand. Under no circumstances should you touch this guy. Because if you do, if your fingers touch his fingers, something terrible is going to happen. You will both disappear. Poof! And when I say disappear, I don't mean some magic trick with smoke and mirrors. I mean a flash of light so bright it would blind anyone looking in your direction for 100 miles. You and your double will turn into pure energy. Bam. No leftovers, no ash. Not even the buttons from your coat will remain. It will be an explosion that makes a nuclear bomb look like a kid's firecracker on the 4th of July. Why? Because your double is made of antimatter. You've probably heard this word in cheap science fiction movies. There's usually some villain with a canister that glows a spooky blue color, and he's threatening to blow up the White House. Hollywood loves that stuff. But let me tell you something. Reality is far crazier than anything a screenwriter can come up with. You see, we're used to thinking that matter is something solid. The table you're sitting at, the screen you're looking at, the hamburger you had for lunch. It's all made of atoms. Protons, neutrons, electrons. We call this stuff. It's what our universe is built from. It's the norm. But nature, oh, nature loves to play games with us. She loves symmetry. And one day she asked us a question. Why does everything have to be exactly this way? Why does the electron have to be negative? Why does the proton have to be positive? What if we flipped it all around? Imagine a world where everything is opposite, where the atomic nucleus is negative and positive electrons fly around it. If you looked at this world from a distance, it would look exactly like ours. Water would be wet, the sky would be blue, and baseball would be just as boring on TV. But if you tried to bring a piece of our pie over there, a catastrophe would happen. Matter and antimatter hate each other. They cannot coexist. When they meet, they annihilate. That's a beautiful word, isn't it? Annihilation. It means the complete destruction of mass. 100% of your mass turns into light. Einstein wrote his famous equation, E equals mc squared, for exactly this moment. And here's what keeps me up at night. This isn't just a theory. It's not a fairy tale. These things are real. They're here. Right now, while we are talking, tiny particles of antimatter are zipping through this room, maybe even right through you. But you know what the most amazing thing about this whole story is? Usually in physics, we find something first. We trip over a rock, pick it up, and say, wow, look at this weird rock. We look through a telescope and see a new planet. The experiment comes first. But with antimatter, it wasn't like that. Nobody was looking for it. Nobody even suspected it could exist. We didn't find it in a laboratory. We found it at the tip of a pencil. This whole crazy idea about a mirror universe started with one man sitting in a quiet room in Cambridge, staring at an equation that refused to behave itself. He looked at his notes and saw something there that made absolutely no sense. And instead of erasing it, he decided to trust the mathematics more than his own eyes. Let me tell you about Paul Dirac. He was a strange guy. I met him a couple of times. He was the complete opposite of me. I like to talk. I like to make noise. I like to play the bongos. Dirac? If he said 3 words in an hour, that was considered a long speech. He was the quietest man in physics. But inside his head there was a revolution going on. The year was 1928. We had a problem. A big problem. You see, we had 2 great theories. On one side, quantum mechanics, which describes tiny things like electrons. On the other, Einstein's theory of relativity, which describes fast things, things flying at the speed of light. And these 2 theories were not talking to each other. They were like a divorced couple that couldn't be in the same room. Dirac wanted to reconcile them. He wanted to write an equation for the electron that would work in the quantum world and at speeds close to light. And he did it. He wrote his famous Dirac equation. It was short, elegant, beautiful, You could carve it on a stone. But when Dirac looked at the solution to his equation, he saw something that made him scratch his head. You know, it's like in algebra class. If I ask you, what is x equal to if x squared is 4? You say 2. And you'd be right. 2 times 2 is 4. But any math teacher will tell you that you forgot the second part of the answer, minus 2. Minus 2 times minus 2 is also 4. Usually in physics, when we get a negative answer for something like energy or mass, we say, oh, that's just mathematical garbage. We throw it in the trash can, because what is minus 3 apples? It's nonsense. You can't have a negative amount of stuff. The Dirac equation gave him 2 solutions for the electron. One normal, an electron with positive energy. Everybody's happy. And one crazy one, an electron with negative energy. Imagine you check your bank account. You expect to see money there, but instead, you see a huge minus. You're in debt. Negative money is real enough. Ask anyone with a mortgage. But negative energy in nature, that seemed impossible. Everyone told Dirac, Paul, just ignore the minus. The equation is good, just throw out the extra bit. But Dirac was too honest for that. He couldn't just close his eyes. He understood one thing that many people forget. Mathematics doesn't lie. If the equation is the language of nature, then nature was trying to tell us something. The equation was smarter than its creator. It was screaming at him, hey, this isn't a mistake. This is a new reality. And Dirac took the boldest step in the history of physics. He said, this minus is real. He proposed that this negative solution describes something we've never seen before. A particle that is a mirror image of the electron. It has the same mass, the same spin, but it has a positive electrical charge. Colleagues thought he had lost his mind. Inventing a new particle just because you have an extra minus sign in your notebook? That's audacity. But 4 years later, in 1932, Carl Anderson at Caltech caught one of them in his cloud chamber. He saw a track of a particle that behaved like an electron but curved the other way in a magnetic field. Dirac was right. The math was right. We discovered antimatter not with our eyes but with our minds. But this creates a new problem, a huge problem, because now that we know this thing exists, we need to understand what it is. And this is where the real headache begins. Because the simplest explanation, it's just an electron with a plus sign, doesn't actually explain all the weirdness. To understand what a positron really is, we need to stop thinking about particles like little billiard balls. We need to do something completely illegal from the point of view of common sense. We need to play with time. All right, hold on to your chairs. Because right now, we are going to break the main rule they taught you since kindergarten. The rule that time flows only in one direction, from the past to the future. Yesterday you were younger, tomorrow you will be older. You break an egg, and it never reassembles back into the shell. This is called entropy, this is called the arrow of time. But here's the catch. When we look at the equations of quantum electrodynamics, the equations describing the behavior of light and matter, they absolutely do not care about this rule. The letter t in the equation is just a variable. You can put a minus sign in front of it, and the equation keeps working. When I was a young grad student, I looked at the Dirac equation and tried to figure out what the hell it meant. And it hit me. Let's imagine you're watching the Super Bowl. Sunday evening, Giants on the field, everyone running for a touchdown. You're watching the game live. Time goes forward, players run forward, everything is normal. Now imagine you have a tape of this game and you hit the rewind button. What do you see? You see players running backwards. You see broken helmets coming back together. The movements look strange, unnatural. But in the world of subatomic particles, there are no unnatural movements. If an electron flies from point A to point B, and we rewind the tape, it looks like it flies from B to A. But there is one nuance. When you change the direction of time in the equation, you also have to flip the sign of the electrical charge. And then it struck me like lightning. What if the positron, that mysterious antiparticle Dirac predicted, is not a new particle at all? What if it's just a good old electron traveling backwards in time? Think about it. An electron with a negative charge flying backwards in time is mathematically indistinguishable from a positron with a positive charge flying forwards in time. It is the same thing, To a detector, to a cloud chamber, to your eyes, it looks like antimatter. But to the universe, it's just an electron that decided to pull a U-turn on the highway of time and drive in the oncoming lane. At this moment you should say, Richard, you're nuts. That's garbage. Things don't travel in time. And you know what? You'd be right. It sounds like total insanity. But the math doesn't care if I'm nuts or not. It doesn't care about your common sense. It works. When I proposed this idea, people looked at me like I was an idiot. Hey, Feynman, you're saying the future can affect the past? In a sense, in the micro world, yes. Imagine an electron flying forward in time, living its life, and then suddenly it collides with something powerful. Bam! And bounces back into the past. At that moment of the U-turn, we see the creation of a pair. We see an electron and a positron appearing as if out of nowhere, but in reality, it is one continuous line looping in time, like a thread in a sweater. This isn't just philosophical jibber-jabber. This idea, antiparticle as a particle going backwards, allowed us to simplify calculations by a factor of 1,000. Instead of messing around with Dirac's infinite seas of particles and holes, we just said, okay, we have two-way traffic. But if we have particles that can move forward and backward in time, how, for heaven's sake, can we depict this on paper? Describing it with words breaks your tongue. Describing it with equations explodes your brain. We needed a new language, a language of pictures. I started drawing doodles on napkins, simple lines, arrows, and these childish drawings turned out to be the most powerful tool we have. You know, I always had one problem with physicists. They love to complicate things. In the 1940s, if you wanted to calculate what happens when two electrons repel each other, you had to write formulas on 10 pages. It was like trying to fill out a tax return for the IRS, only in ancient Latin and in the dark. It was a nightmare. The calculations were so long that by the end of the page, you forgot where you started on the first one. And me? I'm a simple guy. I think in pictures. If I can't visualize the gears turning in my head, I don't understand how it works. I need to see it. So I stopped looking at formulas and started drawing. I said to myself, let's simplify this to the limit. Let time go from bottom to top, and space goes from left to right. Here flies an electron. I draw a straight line with an arrow pointing up, forward in time. Here flies a photon, a particle of light. I draw a wavy line like a little snake. They meet. The electron emits a photon and changes direction. I put a dot where the lines connect. It looked like kids' doodles. Tic-tac-toe. But hidden in these doodles was incredible power. Because remember our crazy idea about time travel? On my diagrams, this was solved effortlessly. How do you draw a positron? Very simple. You draw the same electron line, but you point the arrow not up but down, against the flow of time. Everything became obvious. If you see an arrow going backwards, that's antimatter. You don't need complex matrices. You don't need imaginary numbers. You just look at the picture and see, aha, here they collided, here a pair was born, and here they annihilated each other. I was so excited about this that I went to a conference in the Pocono Mountains to show it to the greatest minds of the time. Niels Bohr was there, Oppenheimer, all the heavyweights. I went up to the blackboard, picked up the chalk, and started drawing my lines and arrows. And you know what? They tore me apart. Bohr stood up and started saying I didn't understand elementary quantum mechanics. They looked at my drawings like I had brought comic books from the Sunday paper to a serious scientific gathering. My colleagues at Princeton snickered. Feynman is drawing his pictures again, like in kindergarten. They thought real science had to be complicated, teeth-grinding mathematics, not funny pictures. But here's the thing, my funny pictures worked. While others spent months calculating a single interaction, I could do it in half a day on a napkin in the cafeteria. My diagrams turned hellish algebra into simple topology. The irony is that these exact childish drawings eventually won me the Nobel Prize. Today you won't find a single blackboard in any university in the world, from MIT to Berkeley, that doesn't have these diagrams on it. It became the language of physics. We stopped speaking the language of equations and started speaking the language of arrows and loops. And these diagrams allow us to see the most terrifying event in nature. Look at this knot. Here is the line of matter. Here is the line of antimatter. They are heading toward each other. They meet at a single point. And after that point, There are no more lines. They cut off. Instead, out flies a wavy line. Light. Gamma rays. We drew this on paper, and it looks harmless. Just a dot on a sheet. But in reality, at that place where these lines converge, there is a release of energy on a scale our brains can barely process. Let's put down the chalk and talk about what happens when these lines intersect not on a blackboard, but in the real world. Because out there, everything burns. Everyone knows Einstein's formula. E equals mc squared. You've seen it on t-shirts, on mugs, maybe even on tattoos, on some hipsters in Brooklyn. But let me ask you, do you really understand what it means? C is the speed of light. A huge number. C squared is a number that will make you dizzy. This formula tells us that locked inside a tiny piece of matter is a monstrous amount of energy. But here's the problem. Getting that energy out is incredibly difficult. Take gasoline. You put a gallon of gas in your Ford, you burn it. Chemical reaction. Do you know how much mass actually turns into energy of motion? A tiny fraction of a percent. Almost zero. It's inefficient. It's wasteful. Then we got smarter. We discovered nuclear reaction. We built a bomb that we dropped in the desert of New Mexico. I was there. I saw that light. We were splitting uranium or plutonium atoms. Was it powerful? Oh yes. But even in a nuclear explosion, less than 1% of the bomb's mass turns into pure energy. Less than 1%. The rest is just hot garbage, radioactive waste. It's like buying a ticket to a baseball game, watching the first pitch, and going home. You miss the whole show. Now imagine antimatter. When matter meets antimatter, nature stops playing around. No 1%, no leftovers, 100%. The entire mass of the proton and the entire mass of the antiproton disappear completely. They turn into pure, furious light. And let me give you an example so you can feel the scale. Imagine a paperclip, a regular office paperclip that weighs 1 gram. If I turn this paperclip into pure energy, do you know what will happen? The explosion will be equal to the power of the bomb dropped on Hiroshima. 1 paperclip. And if we have a pound of antimatter, say, the size of a grapefruit, that's enough to wipe all of New York, Long Island, and probably part of New Jersey off the face of the earth. You think nuclear weapons are scary? Nuclear weapons are children's toys compared to annihilation. It is the densest energy source in the universe. Nothing can be more powerful. Physics simply doesn't allow it. It is the absolute limit. That is exactly why the engineers in Star Trek use antimatter for their engines. Because if you want to fly to the stars, chemical rockets won't help you. You need the fuel of the gods. But when you realize how powerful this stuff is, a chill should go down your spine. Because this isn't just cool fuel. It's the universe's self-destruct button. If matter and antimatter hate each other so much, and if they explode at the slightest touch, then a very, very uncomfortable question arises. We know this stuff exists. We can create it in a lab. We know how it explodes. So why are we still alive? We have arrived at the biggest mystery in modern physics. We call it the Great Disappearance. And believe me, compared to this, any detective novel will seem like a boring newspaper clipping. Let's rewind the tape back. Not just to yesterday, but to the very beginning. To the Big Bang. At that moment when the universe was hot, dense, and very, very loud. Physics gives us an ironclad rule. When you create matter from pure energy, you cannot cheat. You cannot create just an electron. Nature demands balance. You are obligated to create a pair, an electron and a positron, a particle and an antiparticle. It's like flipping a coin. You can't get heads without having tails on the other side. So in the first fractions of a second after the birth of the universe, it was a perfect soup. 50% matter, 50% antimatter. The balance was perfect. And that should have been the end of the story, because, as we just found out, when these guys meet, they explode. Soon after the Big Bang, the universe started to cool down. Particles started to collide, and they should have destroyed each other, every last one of them. Matter should have killed antimatter, and antimatter should have killed matter. The result should have been an empty, boring universe filled only with photons. No stars, no planets, no tax collectors, and certainly no Richard Feynman telling you these tall tales. But look around. Look at your hands. Knock on the table. All of this exists. All of this is made of matter. We won. Antimatter lost. But how? Where did it go? This is what keeps physicists from sleeping at night. We call it baryon asymmetry, but basically that's just a fancy name for the phrase, we have no idea what happened. There is one theory I like. It's scary, but beautiful. Imagine that nature is a casino in Las Vegas. And usually, the casino always plays fair on this issue, 1-to-1. But what if at the very beginning, in that fiery chaos of creation, nature cheated a little bit? Just a tiny bit. What if for every billion particles of antimatter, there were born 1 billion and 1 particle of matter? Imagine this battle. A billion antiparticles collide with a billion particles. Bam! The greatest fireworks display in history. They annihilate, turning into pure light. By the way, that is the light we see today as the cosmic microwave background. But that one extra guy, he had nobody to dance with. His partner didn't show up. He was left alone. And this 1 in a billion, that is everything we see today. All the galaxies, all the nebulae, all the oceans, all the people. We are all made of those tiny leftovers that survived the great massacre at the beginning of time. Think about that for a second. By all laws of statistics, we shouldn't be here. Our existence is a mistake. We are a cosmic error, a typo in the contract, a rounding error at the 10th decimal place. If nature were perfectly symmetric, we wouldn't exist. We exist only because the universe is a little bit lopsided, a little bit imperfect, and thank God for that imperfection. But you know, there is another possibility. Physicists are suspicious people. We don't like it when something just disappears without a trace. We ask, are you sure the antimatter is gone? What if it didn't go anywhere? What if it just moved to a different neighborhood? The universe is a very big place. Who said all of it has to be built from the same bricks as our solar system? Maybe out there in deep space there are mirrors we'd better not look into. Here's a $1,000,000 question for you. If a neighboring galaxy, say Andromeda, were made entirely of antimatter, how would we know? You take your telescope, point it at a star, and look. What do you see? You see light. Photons. But here's the joke. A photon has no charge. A photon is its own antiparticle. Light from a regular star and light from an anti-star look exactly the same. The spectrum is the same. The color is the same. If our sun were replaced by an anti-sun tomorrow, we wouldn't even notice the difference until the solar wind reached Earth. Then, of course, we'd have problems. But just looking through a telescope, no difference. That's scary, isn't it? Space could be like a minefield. You fly to a planet that looks like the Garden of Eden, blue water, green forests. You land, take a breath, and kaboom, game over. Scientists argued about this for a long time. Maybe the universe is like a patchwork quilt. Here is a patch of matter, and over there, across the fence, is a patch of antimatter. Like New York, here's one neighborhood, you cross the street, and you're in a completely different world. We even wondered, what about gravity? If I take an anti-apple and let it go, will it fall down like Newton's apple? Or will it fly up to the ceiling? Most of us bet money that it will fall down. Einstein says gravity doesn't care about charge, it only cares about mass. But honestly, we've never had enough antimatter to roll it into a ball and check. That would be a very expensive experiment. But back to the patchwork quilt. Why do we think big galaxies of antimatter don't exist after all? Because space isn't an empty room. There is gas, dust, wandering atoms out there. And if there were a border between our territory and the territory of the anti-guys, there would be constant skirmishes at that border. Gas clouds would collide with anti-gas clouds. We would see huge glowing rings in the sky, boundaries of annihilation. We would detect massive gamma radiation coming from these fronts. We pointed our detectors at the sky, expecting to see these cosmic fireworks. And you know what we saw? Silence, darkness. The universe looks suspiciously calm. This tells us that most likely there are no anti-galaxies in the neighborhood. Within a radius of billions of light years, everything is clean. We are alone here. Our matter is a monopoly. This brings us back to the thought that antimatter really did disappear. Or maybe we are looking too far away. We build giant telescopes to look at the edge of the universe. We build colliders costing billions of dollars to catch these particles. But nature, she has a great sense of humor. While we look through telescopes, she hid a source of antimatter right under our noses. You don't need to fly to Andromeda to find positrons. You don't even need to leave your house. In fact, you might just need to go into the kitchen. I'm serious. Put down the telescope and pick up a banana. Because what happens inside that yellow fruit is much more interesting than any sci-fi movie. Do you like bananas? I do. Convenient packaging by nature, tasty, nutritious. Everyone knows bananas are full of potassium. Moms tell us this since childhood. Eat it, it's good for your muscles. But moms usually forget to mention one little detail. A tiny percentage of that potassium is the isotope potassium-40. And it is radioactive. Not heavily, don't worry. You don't need a lead suit to go to the supermarket, but this potassium-40 is unstable. It decays. And once in a while, in rare cases, it decays via a process we call beta plus decay. And what flies out of the atom at that moment? That's right, a positron, antimatter. Here's a fact you can tell at the next party if you want everyone to shut up and look at you. On average, a regular banana emits a positron about every 75 minutes. Think about that. The fruit on your kitchen counter works as an antimatter generator. You eat it, and now that generator is inside you. The potassium spreads through your body, and every hour or so, somewhere inside you, an antiparticle is born. It flies a tiny distance, crashes into one of your electrons, and bam, a microscopic annihilation happens. Right now, while you sit and listen to me, you are glowing a little bit from the inside with gamma rays. You are essentially a walking, breathing nuclear reactor on very, very low power. But we went further than bananas. We humans are amazing creatures. We take the deadliest things in the universe and turn them into tools for saving lives. Have you heard of PET scans? Doctors use them to look for tumors or study brain function. That acronym, PET, stands for positron emission tomography. Yes, that same word. Here's how it works. You go to the hospital. The nurse gives you a special solution to drink, usually glucose with radioactive fluorine. Your body thinks, oh, sugar, yum yum, and sends it to where energy is needed most, like the brain or, unfortunately, a cancer tumor. And this fluorine starts to decay. It shoots positrons right inside your head. These positrons can't fly far. They immediately find the electrons of your body and annihilate. Bam, bam, bam. Millions of tiny matter-antimatter explosions every second. These explosions send gamma rays in opposite directions, and the scanner catches them and builds a picture. So when the doctor shows you a picture of your brain and says, look, here is activity, he is actually showing you a map of antimatter annihilation. Next time you see a bill from an American hospital for a scan, and there's a number with 3 or 4 zeros, don't get too mad. After all, you are paying for the most exotic show in the universe. You are paying to tame the very force that could destroy a galaxy and make it paint portraits of your thoughts. It's incredible if you think about it. We went from an equation that seemed like a mistake to a medical procedure that saves lives every day. But I have one last story for you. One idea. And compared to it, bananas and medical scanners will seem like boring accounting reports. This idea is so crazy that when I first voiced it to my professor, he almost kicked me out of his office. I asked him one simple question. John, have you ever wondered why all electrons are absolutely identical? And the answer we found will flip your understanding of reality. One day when I was still a grad student at Princeton, my phone rang. It was my thesis advisor, John Wheeler. And he told me something that almost made me drop the receiver. But first, let me ask you a question. Have you ever wondered why all electrons in the universe are absolutely identical? Look at people. We are all different. Look at Ford cars. Even if they came off the same assembly line, one has a scratch on the bumper. The other's engine sounds different. But electrons? Oh no. Every electron in the universe is an exact copy of any other. The same mass, the same charge, the same spin, down to the last decimal point. You can't brand an electron. You can't say, hey, that's the same electron I saw yesterday. They are indistinguishable. Why does nature stamp them out with such frightening precision? Why are there no fat electrons or skinny electrons? And here Wheeler says to me on the phone, Feynman, I know why all electrons have the same charge and the same mass. I ask, why? And he answers because they are all the same electron. Let that sink in. One single. Imagine a huge tapestry, the fabric of the universe, space and time. And imagine one long, infinitely long thread. This thread starts at the Big Bang. The electron flies forward in time, lives billions of years, participates in chemical reactions, builds stars, planets, your bodies. It reaches the end of time, the death of the universe. And there it turns around. It flies backward in time. And as we already know, an electron flying backward in time is a positron. It flies back to the Big Bang, turns around again and flies forward. Back and forth, zigzagging through eternity. If you take scissors and cut this tapestry at the moment of now, you will see billions of cross-sections of this single thread. Some sections are the thread going up, electrons. Other sections are the thread going down, positrons. But in reality, it isn't billions of particles. It is one particle tangled into a ball the size of the universe. This explains everything. Of course, they are identical. It's the same guy. The electron currently running through your computer wires and the electron located in a distant galaxy, it is the same creature, just on different loops of its infinite journey. I said to Wheeler, but John, if that's true, then there should be an equal number of electrons and positrons, just as many paths forward as backward. But we see only electrons around us. Where are all the positrons hiding? Wheeler didn't miss a beat. He said, maybe they're hiding in protons or in neutrons? Of course, the theory turned out not to be quite right in the details. We didn't find all those hidden positrons in the quantity required. But the idea itself, the very thought that the complexity of the world might be an illusion created by a single object dancing in time, that changed my view of physics forever. We are used to thinking that we are small and separated. I am here, you are there. My atoms are my atoms, yours are yours. But what if at the deepest level, at the level of the very fabric of reality, we are all woven from the same thread? Literally, this isn't just physics anymore. It's poetry, but it is poetry written in the language of mathematics. Antimatter ceased to be a monster or a destroyer for me. It became part of the harmony. It's just the backswing of the pendulum. Without it, the picture would be incomplete. Without it, we would have one-way traffic, a boring road to nowhere. And this brings us to the most important lesson I learned in my entire life in science. The lesson about how nature's imagination actually works. We've come a long way today. We started with a mirror reflection on the street and ended with the idea that the whole universe might be woven from a single thread. We looked into bananas and saw nuclear reactors there. We looked at equations and saw maps of time in them. And you know what I think? That is the most beautiful thing in this whole story. We didn't invent antimatter because we felt like it. We didn't invent it to write a cool script for a movie. We found it because we followed the logic of nature. We listened to the music the universe is playing, and we just wrote down the notes. People often ask me, Feynman, doesn't the world become boring when you know how it works? Doesn't the rainbow lose its beauty when you know it's just the refraction of light in water droplets? And I tell them, are you out of your mind? Of course not. It becomes even more beautiful, because to the beauty of the colors, you add the beauty of understanding. You look at the world and see not just chaos. You see an incredibly complex, yet elegant game of chess that the gods are playing. We don't know all the rules. We are just watching the board. Sometimes we see a strange move. A piece disappears, or a pawn turns into a queen. We scratch our heads and think, that's impossible. But then we realize, oh, there is a rule. There is a rule that allows this. The discovery of antimatter was exactly that kind of moment. We saw a move that looked illegal, a minus in the equation, a particle going backward, but it turned out it wasn't a mistake. It was part of the great symmetry. Nature loves balance, and she loves to surprise us. Nature's imagination is far, far richer than human imagination. We could never have invented quantum mechanics or antimatter just sitting in an armchair and fantasizing. It's too weird for our human brains. We had to peek at it from reality. So next time you eat a banana, or look at the stars, or just look in the mirror, remember this. Remember that behind this ordinary, solid reality hides a churning ocean of particles being born and dying, traveling in time, dancing their infinite dance of destruction and creation. You are part of this dance. Your atoms, your electrons, they know the rhythm. Don't be afraid of weirdness. Don't be afraid of questions that seem stupid. And most importantly, don't be afraid if your equations give you an answer that seems impossible, because that is exactly where, in those impossible places, the most interesting stuff is hiding. Thanks for spending this time with me, and remember, if you think you understand quantum mechanics, that means you haven't understood it yet. But trying to understand, that's the most fun thing in the world. See ya.